and it is recording.
Okay. Then we're going to call this take 2. Okay, you can start anytime. Go ahead.
All right. If you're responsible for designing, building, or operating machine learning workloads on AWS, what's the best way to know if your workload is well architected? I'm Shelby Eigenbrod, and I'm an AI/ML Specialist Solutions Architect at AWS. We frequently get questions on how to build solutions that adhere to AWS best practices as solutions architects. Today, I'm going to walk you through the AWS WellArchitected Framework, along with the AWS WellArchitected Machine Learning Lens, to better help you understand the question, is my workload well architected? We don't have time to cover every aspect of the framework or of the lens in this session, but I will cover how the machine learning lens relates to the broader AWS WellArchitected Framework. Then we'll dive into some of the details on the machine learning lens, as well as walk through how you can utilize the AWS WellArchitected Framework in combination with the machine learning lens to evaluate your own workloads. First, let's talk about the broader AWS WellArchitected Framework. AWS WellArchitected establishes the framework an approach for customers and AWS partners to use to regularly evaluate workloads and be able to answer the question, are you well architected? The framework is set up across the pillars of security, cost optimization, reliability, operational excellence, and performance efficiency. So these are the pillars that we use to determine if your workload is well architected. Using a consistent approach to evaluate your workloads across these pillars provides several key benefits. Applying the best practices that are discussed in the framework allows you to build and deploy faster on AWS, while making informed decisions using and following the best practices recommended by AWS. And these practices are learned from working with many customers over many types of workloads operating at scale. So in the framework, we cover key design principles and best practices for each pillar. These design principles and best practices apply to all AWS workloads. So what does it mean to be well architected? It means that you've considered and architected for all of these aspects. So things like, how are you going to operate and maintain your production workloads? Have you considered security at all levels of your application? Is your system reliable and resilient from failure? Are you using the most performant resources to run your application efficiently? And then finally, is your workload optimized to deliver business value at the lowest price point? For anyone that's new to AWS WellArchitected Framework, let's take a quick look at the framework structure. So in addition to the pillars, the framework also provides design principles and drives best practices within each of these pillars through a set of questions related to these design principles. So here's a quick sample of what the framework provides. So this is from failure management under the reliability pillar. As you can see, the WellArchitected Framework drives best practices through a set of questions in each area. So in this case, we're asking, how does your system withstand component failure? Each question has some context associated with it to further explain the question. And then you can see the best practices here for this particular question, which include items such as monitoring at all layers, architecting for multiple availability zones, or even multiple regions, depending on your use case, and even creating things like decoupled architectures. So all of the questions for the broader AWS WellArchitected Framework are available in the white papers, but also within the AWS WellArchitected tool, which is available inside your AWS console. In the tool, we also provide a plan on how to architect for the cloud using established best practices based on your responses to the questions that you've answered. So this is a very brief introduction into the AWS WellArchitected, but where does the machine learning lens white paper fit in? Before using a lens white paper, it's really important to understand that broader AWS WellArchitected Framework because, as I previously mentioned, it is intended for use by all AWS workloads. So, however, there are some best practices that can be really specific to a technology domain, like machine learning or analytics, or even to a specific industry, like financial services industry. So for this, we have several Lens white papers that are available and are intended to be used in parallel with the broader AWS Well-Architected Framework. And these help address the design principles and best practices that are really specific to those domains and that industry. A typical question that we often hear is, should I use both the Lens white paper as well as the broader AWS framework? And the answer is yes. We purposely exclude topics covered by the broader framework in the Lens white paper. So to really evaluate your workload, you really need to use the framework along with any applicable lenses. So now that we've covered some information about how the Lens white papers relate to that broader framework, let's dive into the machine learning lens. The machine learning lens is relatively new. It was released in May of 2020. And inside the machine learning lens, we focus on how to design, deploy, and architect your machine learning workloads in the AWS cloud. The paper is intended to cover the AWS machine learning stack, which covers our infrastructure and frameworks, as well as our ML services and our AI services. The white paper takes on the exact same structure as the broader framework. It starts by describing general design principles for machine learning workloads. And then we discuss design principles that are specific inside each pillar. And the pillars are the exact same, from operational excellence, security, reliability, performance efficiency, and cost optimization. One quick note, while the broader framework is available in the AWS console in the AWS Well-Architected tool, the machine learning lens is not yet available. So to perform a review using the lens, you can download the PDF, you can view it in HTML format online, or even through your Kindle device. So you can download that and use that white paper directly in tandem with the Well-Architected Framework to evaluate your machine learning workloads using the questions and best practices in each pillar. So now let's walk through a simple use case to illustrate how you can use the lens to evaluate your own workload. The use case we're going to use for this walkthrough is part of the AWS Solutions Library, and it's focused on customer segmentation using Amazon Pinpoint and Amazon SageMaker to collect customer data and then create pinpoint segments using a machine learning model that is built and deployed using Amazon SageMaker. The idea here is that we'll then use those segments to create tailored messaging for our customers. And you can see within this solutions architecture, there's multiple components in this solution, and that's pretty typical of any solution that utilizes machine learning. And we don't really have time to dive into each of these, but we will go ahead and show how you can use that machine learning well-architected lens to evaluate this workload against AWS best practices. To do this, what we'll do is we're going to walk through each pillar and review the design principles of each pillar, and then we'll cover a few sample questions in the context of that customer segmentation use case we just talked about. When it comes to the security pillar, these are the high-level design principles. You can see they're focused on data governance and lineage, as well as specific considerations for restricting access to machine learning systems, as well as enforcing regulatory compliance. Let's take a look at a sample question in the machine learning security pillar. How are you protecting machine learning models? So for this use case, let's take a look at a few recommendations from the lens to apply, including data encryption and least privilege-based access. For data encryption, we look at the data that should be encrypted in transit as well as at rest to protect our trained models. For our data in transit, requests to the SageMaker API and console are all automatically made over a secure SSL connection. For our data at rest, our input data feeding into the model training is covered under that broader recommendation as part of the broader framework to encrypt your data at rest. However, for machine learning, we should also consider configuring our notebook and our batch transform jobs to have encrypted storage volumes attached as well. And then we also want to ultimately protect our model artifact that's stored in S3. So SageMaker will use the default KMS key for S3, but you can also optionally consider whether you prefer to bring your own KMS key for encryption. Let's move on to the next recommendation of ensuring the principle of least privilege is in place, which essentially means only grant access to the roles or users that need access. And then within that, ensure that those roles and users are only authorized to perform the minimum set of actions needed to perform a specific task. So in this scenario, we want to protect our model by ensuring we have a policy that enforces minimum privileges set up not only for our model artifact, but for consumption of our model as well. So as an example, We may want to set up our permissions so that a data scientist or even an automated pipeline can put new model objects to our S3 bucket. But then maybe we want to restrict the ability for a data scientist to delete a model artifact from our S3 bucket. You also want to deploy your model so that a consumer of that model can perform inference against it securely. In this particular case, we're using step functions to call our SageMaker batch transform job. So with this, we want to make sure that the execution role that is calling our SageMaker batch job only contains the privileges that are actually needed to run that SageMaker batch job. And maybe any other relevant SageMaker API calls that are needed for this particular step functions workflow. But as an example, you don't need to grant SageMaker full access. You need to scope it down to only the API calls that are required to perform this specific task. And keep in mind when you're going through these security questions within the AWS well-architected machine learning lens, that these practices really layer on top of each other. So to get that defense in depth, we recommend using the security pillar, the well-architected framework in whole. As an example, there are recommended practices around data classification that also provide benefit in terms of the protection of your trained machine learning model. So this was just a quick sample inside security, but let's move on to cost optimization. So these are the high-level design principles associated with cost optimization. As with other workloads on AWS, we recommend using managed services to reduce the cost of ownership. Next, while machine learning workloads benefit from high-quality training data sets that are relatively large, we do recommend starting with smaller data sets on small compute or even your local compute to be able to quickly iterate at low cost. And then after that experimentation period, consider scaling up to train with a full data set or even training on distributed compute nodes. Also, another recommendation is when you're training with that full data set, consider streaming data into your training cluster instead of storing the data directly on the training cluster node to reduce those storage costs. Next up, right-sizing notebooks, training, and model hosting instances. For model training and hosting, the recommendation there is to experiment to determine the optimal compute capacity needed. Once again, recommend starting with smaller instances, measure that resource utilization, and then adjust as needed. Also measure the differences between CPU and GPU needs during training and inference. While some machine learning models may require heavy GPU instances during training, inferences against that deployed model may not necessarily require the full power of a GPU. Also, take into account what inference architecture should be based on the consumption pattern for your model. So some models, such as fraud detection, need to be available up and running 24/7 for real-time predictions, while others, such as forecasting, may only need to be available periodically. So in the first case of fraud detection, that cost of a 24/7 real-time persistent endpoint is justified. Whereas with a forecasting use case, you could take advantage of lower cost batch jobs, which we are essentially spinning up resources for you automatically, spinning them back down when they're no longer in use. Then finally, define the overall return on investment and opportunity cost. To do this, there's a few things to consider. First, weigh the cost of adopting machine learning against the opportunity cost of not leaning on ML transformation as you work through selecting the right machine learning projects to include and really drive those business outcomes. Secondly, specialized resources such as data scientist time or even the model time to market might be your most expensive and constrained resources. So in this case, the most cost-effective hardware choice might not really be cost optimized if it constrains the experimentation and the time to market for a particular model. So let's take a look at a sample question inside the machine learning cost optimization pillar. How do you optimize costs for machine learning inference? And we talked a little bit about this, but to answer this, you really need to consider things like latency, throughput, the time that a prediction endpoint needs to be up. And a key thing to consider here is whether you actually need that persistent real-time endpoint or you can take advantage of batch processing. And the reason for this is a real-time persistent endpoint is going to be up and running 24/7 and accruing costs while it is up and running. For periodic prediction, SageMaker batch transform jobs are better suited for that particular use case. So look at your use case and determine whether you need a real-time endpoint or if you can take advantage of batch transformation jobs. In the case of this particular solution, it's set up to use batch predictions that use SageMaker's batch transform jobs So assuming this is providing the intended results for our customer segmentation use case, a real-time endpoint isn't needed here, and a batch job is the right choice. Because we're using batch processing, auto-scaling considerations don't really apply, but right sizing of compute in terms of this batch transform job absolutely do. So it's important to take advantage of the metrics that get emitted, so things like CPU, GPU utilization, to be able to optimize the compute cost without over-provisioning. So this was just one of the questions under cost optimization, but check out the full white paper as well as the broader AWS WellArchitected for cost optimization recommendations. Let's move on to the performance efficiency pillar. So these are the high-level design principles associated with the performance efficiency pillar in the ML lens. This pillar really focuses on the efficient use of compute resources to meet your performance requirements. To do this, we recommend taking a data-driven approach to selecting your high-performing architecture. We also recommend that you regularly review your choices to ensure that you're taking advantage of the continuously evolving AWS services. Let's take a look at one of our questions inside the performance efficiency pillar. Now, the performance efficiency pillar in the machine learning lens relies heavily on the broader framework. So as many of the broader considerations for performance efficiency don't really change just because it's a machine learning workload. However, there are a few unique considerations. Let's take a look at one of those questions here. How do you scale your machine learning workload while maintaining optimal performance? Some considerations in this area include whether or not you're using a managed service like SageMaker or you're using one of our deep learning AMIs running on EC2. In this scenario, we're using SageMaker XGBoost, which is going to automatically emit some metrics regarding things like model latency. And if this was a persistent real-time endpoint, we could also add on SageMaker Model Monitor to measure model performance over time. Another consideration here would be to take advantage of elastic inference as applicable. This is a great option for hosting your models on CPU while still being able to tap into the power of GPU when you need it. In this case, we're running XGBoost and CPUs on batch mode, so this one doesn't really apply to our workload. But finally, in this scenario, we could take a look at our distributed training options. In this case, again, we're using XGBoost, so we probably want to see which way we're using XGBoost with SageMaker. SageMaker supports XGBoost through built-in algorithm as well as the open source version. The open source version has a more efficient implementation of distributed training, which enables it to scale out more effectively and reduce out-of-memory errors. So this may be beneficial if we look into our performance metrics and we see that our existing training job isn't able to scale. So we'd want to look into this, see what version we're using, seeing if there are any training performance bottlenecks, and then be able to optimize if needed. All right, let's move on to operational excellence. So in the next few slides, we're going to focus on operational excellence, starting with the design principles. Just as is true for all the pillars of the MLNs, the operational excellence pillar really builds on top of the operational excellence pillar for the broader AWS WellArchitected Framework. In the lens, again, we only focus on the principles that have unique considerations for machine learning workloads. To highlight a few of those, we focus on establishing cross-functional teams with roles that are unique to machine learning, such as data scientists or researchers that may not have IT backgrounds. Another example is looking at the unique considerations for monitoring machine learning workloads, where not only are you employing standard system monitoring for things like CPU or GPU utilization, but you're also looking at monitoring for things like model drift or data drift. And then finally, automating your machine learning pipelines and establishing a versioning strategy for your machine learning inputs, such as training data, as well as a versioning strategy for your packaged artifacts, such as that deployable model. So let's take a look at a few pillar-specific questions and responses. Starting with, how have you prepared your team to operate and support a machine learning workload? Often in a machine learning project, there may be resources that have never deployed or operated a workload in production. And similarly, the teams that may traditionally deploy and operate workloads may have very little experience with machine learning or machine learning workloads. Additionally, machine learning code is typically a very small part of an overall solution. Like we see here, there are many integration points and dependencies to consider when managing this overall machine learning workload. To help prepare your team to operate and support a machine learning workload, we recommend 1, providing high-level cross-training to the teams that will develop and operate and deploy these models. The goal isn't to make a deployment engineer a data scientist or vice versa, but to provide enough education to the teams that enable them to effectively build, deploy, and operate models and provide that path to production for your machine learning workloads. Second, establish cross-functional project teams early. This includes all stakeholders that are required to build, deploy, integrate, and manage the workload in production. The team should have a clear view of the overall machine learning problem as well as the operating model for the solution. Next, we want to evaluate how do you know when to retrain machine learning models with newer updated data. And this ties to another question about model monitoring in the lens, but with this question specifically, what we're really diving deeper here on is identifying the retraining strategy, whether it's metric driven based on indicators like model or data drift, or if it's driven based on an event like new training data. Regardless of the strategy, we just want to ensure that we aren't incurring any technical debt of decaying models without having that retraining strategy in place. Next, we'll cover our final pillar, reliability. Again, in the lens, we focus only on the principles for reliability that have unique considerations to ML. Many of the principles for reliability are covered in the broader framework, so we don't repeat them here. It leaves us with really two key design principles specific to machine learning, including first, managing changes to model inputs through automation. And this refers to ensuring all inputs that are used to train and host a model are traceable and versioned through automation. For training, this includes not only the versioning of the model inputs like code, hyperparameters, or Docker images, but also versioning of the corresponding training data. For deployment, this refers to the inputs that are required to set up your model hosting environment for predictions, which can include the deployable model artifact, as well as any inference or helper code or serving code. Ensuring end-to-end traceability across that lifecycle allows for recoverability in the event of any system failure or human error. Second, train once and deploy across environments. This is similar to the build once, deploy anywhere strategy that we practice with our software development environments. But in this case, we're ensuring that we train once using the same, and we use that same packaged model artifact to deploy to multiple environments. We do this to avoid bringing any unexpected changes into the model as we deploy across our environments. Let's take a look at a pillar-specific question within reliability. How do you recover from failure or inadvertent loss of a trained model? This question focuses on the mechanism of providing or protecting inputs and artifacts that would be required to recover in the event of failure or inadvertent loss of that trained model. As a best practice here, we recommend first ensuring that inputs and resulting artifacts are versioned so that it's possible to recover to a specific point in time. And this includes your training data, your Docker images, your hyperparameters again. Second, implement preventative controls that are aimed at really protecting those artifacts that are required for recovery. So as an example, if you're using Amazon SageMaker, the model that is stored in S3 should have access controls implemented to prevent modification or inadvertent deletion. Finally, reducing the amount of human intervention not only minimizes accidental loss, but also ensures repeatable deployments, so adding in additional automation. You can check out the other questions and practices within the lens that are related to reliability, as well as the other pillars that we discussed here today. But to wrap it up, here are a few resources, including the broader AWS WellArchitected Framework that we discussed at the beginning, and the machine learning lens. Again, these two should be used together to evaluate your workloads. We went through a lot in a short amount of time, but hopefully you were able to take away some tips on how you can use the AWS WellArchitected Framework in combination with the Machine Learning Lens white paper to answer the question of, are you well architected? Thank you so much for your time and hope you enjoy the remainder of the conference.
Awesome. Great. So I'm going to stop the recording.
All right.
And then we're going to give it a little bit to upload. It's going to take a little time to upload from your phone. So you can stop your recording